In section 7.3, we're going to be using all of the trig identities that we've learned so far to prove some new trig identities. And a trigonometric identity is just an equation that contains trig expressions. That's always true, no matter what you plug in for the angle. So in section 7.1 and 7.2, we looked at some very common ones that we can group into categories such as Pythagorean identities, sum and difference identities, double angle identities, half angle identities. But there are tons and tons and tons and tons of trig expressions that have an equivalent way that they can be written. And technically, if I can set one trig expression equal to another one that it's equivalent to, it's considered a trig identity. It's some sort of an equation with trig in it that's always true. Now, it might not be one of the basic ones that falls into one of the categories that we learned in section 7.1 and 7.2. So we didn't talk about it in 7.1 and 7.2, but we can use those basic identities to help us prove that these new ones are true. And that's what we're trying to do here in 7.1 and in 7.3. So there's a couple ways that we can go about this. So we're going to pretend we have some f of x equals g of x. These are our trig expressions. And our goal when we prove trig identities is to get them to match. Now, we are never going to move anything from the right-hand side to the left-hand side or vice versa. Everything from f of x is going to stay on the left. Everything from g of x is going to stay on the right. So sometimes what I like to do is I like to put a separator line right down the middle. So we don't ever move anything from side to side. What you can do, though, is sometimes one of these is pretty simple. So let's say g is already a fairly simple expression, but f is pretty complicated. Usually, whichever expression is more complicated, that's going to be the expression that we can do more manipulating with. It's going to be the one that we can use more trig identities to do kind of more massaging and more playing with. So one option is to just leave g alone and manipulate the f. Algebraically, and with trig identities until it matches g. And you just keep doing this on and on and on forever until you have g of x equals g of x. Once you have the same exact thing on both sides of the equation, you have proven the identity. And you don't want to stop before that. You want to work it all the way down until both sides of the equation say the exact same thing. And now it doesn't matter what's on either side, so it's possible that the f is the easy side and the g is the more complicated side, so we'll just work with g. It's also possible that both sides are kind of complicated, and we're going to play a little bit with both of them. And then we're going to manipulate both and turn them both into something different. And that's perfectly fine as well. We're going to use algebra and we're going to use trig, and we're going to turn them both into something different. As long as we can get them to match using algebra and using trig identities, the basic trig identities we learned in 7.1 and 7.2, as long as we don't violate any math rules, and we can get them to match, we've proven the identity. So you've got two options here. You can just leave one of them alone if it's already pretty simple, and then just keep working with the other one until it matches. Or you can play with both of them until they match. What you cannot do is move things from side to side. We do that a lot in algebra. We move things from the left and the right in order to solve. We are not trying to solve here. We're just trying to get both sides to match. So the right-hand side is its own little simplification problem. The left-hand side is its own separate simplification problem. Don't try to move things from side to side. They are like two separate entities. So I'm going to do a couple of these by hand, but then what I'm going to do after that is I'm going to go into MyLabs Plus, because working these in MyLabs Plus is a little bit different. You don't have the freedom to kind of pick and choose what you want to do. They kind of guide you along the way. And since you're going to be taking a test on this week, I wanted to run through some of those problems with you that you saw in your homework in case you had any trouble with them, and help you with how MyLabs Plus wants it to be done. So we're going to do two here by hand, and the directions are to prove each identity. They're just like simplification problems, except with simplification problems, you just keep going until till you think it looks as nice as possible. And back in 7.2, we had some rules to decide if it was as simple as possible. Here with identities, I think identities are easier. It's easier to decide when you're done. You're done when both sides match. So for me, identities are easier. I know I'm done when both sides match. Sometimes with simplification, it's harder to tell when you're done. So I know I'm done when both sides match. And these are always going to be equations. So we're going to try to prove that, let's see. Let's start with an easy one. This one is pretty easy. And then we'll do a harder one next. Tan theta times tan theta plus cotan theta equals secant squared theta. We want to prove that this is true. So it is an equation that contains trigonometry. We are told that it's an identity. This equation is always true no matter what you plug in for theta, and we want to use the identities that we already know to show that it's true. We are not allowed to move things from the left to the right. The left is its own problem, the right is its own problem. Now, I am going to point out this side is already, the right-hand side is already fairly simple. There's not a whole lot I can do with it. So I'm going to leave that side alone. It's only a single term. So just for right now, I'm going to leave that one alone. But the left-hand side, I see some things I can do. I see some algebra I can do. I know I can distribute. And then we'll see what happens from there. So I'm going to start just manipulating my left-hand side. And I'm going to start with some algebra by distributing. So tangent times tangent is tangent squared. And then tangent times cotangent, for right now, I'm just going to say tangent times cotangent. And this equals secant squared. Not doing anything with the right-hand side, just copying it down. All right, well, there's a relationship between tangent and cotangent, and this is now where we need to remember our identities. Cotangent is the reciprocal of tangent. So I'm going to use that to help me simplify that second term. Cotangent is 1 over tangent. And if I multiply them together, and I'm going to do this in several steps, it really turns into the fraction tangent over tangent, which is equal to 1. Now, some people would stop right here and say, this is a true statement, tan squared plus 1 equals secant squared. But to prove an identity, you are not done until both sides say the exact same thing. So on the right-hand side, tan squared plus 1, this is a Pythagorean identity for secant squared. And just a little pointer for your test, anytime you see a squared, you should check your Pythagorean identities and see if you can use them. Anytime you see a square, you should think Pythagorean identities. Can I use a Pythagorean identity here? And this one you can, tan squared plus 1 equals secant squared. And now my left and my right match, secant squared equals secant squared, so we're done. So I started at the top by distributing my tan. I got tan squared plus tan times cotan, and then I recognized that these guys are just reciprocals of one another. So I rewrote cotan as 1 over tan and multiplied and got 1. A lot of people are going to stop there and say, that's true, so I'm done, I've done it. But technically, with identities, you're not stopping at a true statement, you're stopping when both sides match. So you need to go one step further. The left-hand side is its own separate problem. At this point, right here, the left-hand side and the right-hand side do not say the exact same thing. So we need to go one step further and say tan squared plus 1 equals secant squared. Now the left and the right say the exact same thing, and we have proven the identity. So let's do another one, and let's do one with fractions. And we are going to try to prove that sin x plus cosine x all over secant x plus cosecant x is equal to sin x over secant x. This one's a little bit harder, only because usually people shy away from the fractions. People are usually very uncertain with their own personal ability when it comes to fractions. So don't worry about the trig being in there right now. What I am going to do is draw my line. I cannot move things from left to right. The algebra that we usually try to do is to clear the fractions. You cannot do that here. You cannot clear the fractions by multiplying both sides by the common denominator. We cannot do that. We cannot cross multiply since I have a fraction equal a fraction. We've got to think of the left-hand side as a problem and simplify as much as possible. We've got to think of the right-hand side as its own simplification problem and get them to match. And that's how we prove the identity. So there is one thing that I'm going to do on the right, and then I'm going to leave it alone. Secant in the denominator, secant is a reciprocal function. So there's one thing I'm going to do, and then I'm going to leave the right-hand side alone and just deal with the left. The left is definitely the much more complicated side, so there's going to be a lot more I can do to manipulate the left-hand side. So I'm going to do this really quickly. Since secant is a reciprocal function, I can write this as sine x over, well, secant is 1 over cosine. And instead of dividing by a fraction, I can flip and multiply. So this is the same as sine x times cosine x over 1, which is just sine x times cosine x. I like that a little bit better. I prefer to multiply than to divide if I have that option. So sine divided by secant is exactly the same as sine times cosine. So my goal here is to get this side to say sine times cosine. Look in the denominator, we've got reciprocal functions. So I'm going to change them. I'm going to change them to their respective sine and cosines, just like I did on the right. I'm going to leave the top alone for now. Sine x plus cosine x. Another reason I'm doing this is because this problem contains 4 different trig functions. Anytime you're working with lots of different trig functions, you can always convert everything back to sines and cosines. So if you're ever unsure what to do and you've got lots of different trig functions, just change everything back to sines and cosines and just work with sines and cosines. Secant, cosecant, tangent, cotangent, they can all be written in terms of sine and cosine. So secant is 1 over cosine, and cosecant is 1 over sine. I can't flip and multiply yet because I've got 2 different fractions. But if I get a common denominator here and get them combined into a single fraction, then I can flip and multiply. So what I'm going to do is I am going to get a common denominator of sine times cosine. So I'm going to multiply by sine here in the top and the bottom. And I'm going to multiply by cosine here in the top and the bottom. And now those denominators match. I'm still leaving my numerator alone for right now. I'm just kind of working with my denominators. So sine x plus cosine x all over. So now these guys match. I can add those numerators. I've got sine x plus cosine x all over sine x times cosine x. Now instead of dividing by a fraction, I can flip and multiply. So your numerator stays the same, but instead of dividing by this fraction, I'm going to flip it and multiply. And these guys are going to cancel. I've got sine x plus cosine x in the top and the bottom. And once they cancel, all I'm left with is sine x times cosine x, which is exactly what I had changed my other side to, sine x times cosine x. Voila. So a good thing to point out on this problem that was a little bit different is because I had 4 different trig functions. I was working with sine, cosine, secant, cosecant. If you're trying to do a simplification or prove an identity and you've got lots of different trig functions in the problem, you can always change everything to sines and cosines and just work with sines and cosines. So we could have thrown some tangents and some cotangents in there as well and made it look even worse. But then at one of our very first steps, just change everything to sines and cosines. And that will help out a lot. So that's one of the first things I did. I changed my secant over here on the right to a cosine, and then I changed secant to a cosine, cosecant to a sine, and then right down here, next couple steps, all I've got is sines and cosines. Started to work out much better. And again, there's a lot of algebra in here, so you've got to be really good with your algebra and your fractions because a lot of these problems do have fractions in them. So working it out by hand on your own is one thing, but then doing it how MyLabs Plus wants you to do it is completely different. So I'm gonna keep my page open here because I might have to come back to have some scratch paper, but I'm gonna open up MyLabs Plus and look at some of the problems that MyLabs Plus is having us do. So in MyLabs Plus, problem number 19 from homework number 4. This is from 7.3. It asks us to prove the identity cosecant x plus 1 over cotan x equals cotan x over cosecant x minus 1. Make sure you read all of the directions in these problems. It is extremely important. I know I've said this before, but a lot of you guys are losing points just because you're not reading the directions and answering the problem how it wants to be the problem to be answered. I, of course, will go in on your tests and give you back credit, if not all of the credit, at least partial credit on a lot of those problems. But it can probably waste a lot of your time on the homework if you keep getting the problem wrong over and over and over again just because you're not reading the directions. So just be really careful with that. And I know it could probably be really frustrating if you take your test and it says a really bad grade and you don't know why. And it's just because of direction stuff, and then I've got to go in later and adjust the grade. But still, just that immediate shock of seeing the bad grade, when really you didn't do that bad. I just have to go in and adjust it. So just read all of the directions. It says to verify the identity, start with the left side. So cosecant x plus 1 over cotan x, and transform it to obtain the right side. So they want us to leave the right side alone. Choose the correct step and transform the expression according to the step chosen. So let's see what our options are. Multiply by a form of 1 over 1. Add and subtract by a form of 1. Add a reciprocal identity. So they want to know what we are going to do. So cosecant x plus 1 over cotan x is equal to cosecant of x plus 1 over cotan x, and they want us to type something in the box next to it. They said only work with the left-hand side right now. Only work with the left-hand side. And they want to know what we're going to start doing. I'm glad I picked this one because this one's a tricky one. What we're actually going to do here, you are not going to add and subtract from a fraction. Then we have to get common denominators and blah, 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 and all that stuff. So you're never going to add and subtract from a fraction. We're not going to do any sort of reciprocal identities yet. We might later on, but what we're going to do right now is we're going to multiply by a form of 1. And I'm going to tell you why. And I'm going to go back over to my notepad here, and I'm going to show you why I'm going to do this. So we've got cosecant x plus 1 over cotan x. Now, we've got an identity that says cosecant squared minus 1, which is a difference of squares. If you remember back to algebra class, the expression x squared minus 1, that could be factored to x minus 1, x plus 1. So this right here is like a trig identity. Cosecant squared minus 1 is like a trig identity. Cosecant squared minus 1 is a trig identity, I'm sorry. But it looks just like x squared minus 1, which factors to x minus 1, x plus 1. We already have part of that factorization in our cosecant x plus 1. If we can just introduce this piece, then we could multiply it out and have the full identity there on the top. This is called a Pythagorean conjugate because we're trying to make a Pythagorean identity by multiplying by the same expression but the opposite sign. And that's what a conjugate is, same expression but opposite sign. So we're going to multiply top and bottom by the same thing. That's why it's a fraction that's equivalent to 1. We're going to multiply by cosecant x minus 1 in the top and the bottom. Now in the top, when we FOIL that out, we get cosecant squared x. The inners and the outers end up canceling. Anytime you multiply conjugates, they cancel because we're going to get a negative cosecant and we're going to get a positive cosecant, which just makes 0. And then negative 1 times positive 1 is a minus 1. In the bottom, I'm not going to multiply out. I'm just going to write those two pieces next to each other for now. Okay, so I've multiplied by a fraction that's equivalent to 1. I'm going to see if my Leb's plus likes this answer or not. Cosecant squared minus 1 over cotangent times cosecant minus 1. And I'm wondering if they want me to simplify in the denominator, or at least distribute in the denominator. So if we distribute in the denominator, our denominator turns into cotangent x cosecant x minus cotangent x. Oh, you know what? They don't want me to put this in yet. I'm just going too far. All they want to know is what fraction I'm multiplying by. There we go. They just wanted to know the fraction that we were multiplying by, which was the Pythagorean conjugate, cosecant x minus 1 in the top and the bottom. And now they want to know what our answer is going to be, which is cosecant squared. This is what I was just trying to type in a minute ago. X minus 1 over cotangent x times cosecant x minus 1. And the drop-down box here wants to know what we did to get that. and all we did is distributed in the numerator. So like I told you, I did not distribute in the denominator because there's going to be some canceling that I can do in just a minute. So all I did is distributed in the numerator. And it might be helpful if you check what your options are in the drop-down box before you do the actual math. And that will give you a clue as to what they want you to do next. So if you look at your options, add a double angle identity. No, we're not working with double angle identities here. We already said we're working with Pythagorean conjugates, so we're probably going to use a Pythagorean identity. No half angle identities. We've already said Pythagorean identity. So we're going to apply a Pythagorean identity to the numerator. So all we want to do is replace the numerator with the Pythagorean identity. Cosecant squared minus 1 is equal to cotan squared. I'm sorry, I'm doing this on a tablet. That's why it takes me long to type things in. Okay, so just don't get ahead of yourself. They just want you to do these tiny little pieces, just tiny little bits at a time. So they went ahead and simplified for us because there's now cotangents in the top and the bottom. So they went ahead and canceled, it looks like, that cotan from the bottom and one of the cotans from the top. And now the drop-down box says simplify in the denominator. Yeah, we did that. We canceled the cotan in the denominator, but that's not all that we did. Cancel common factors. Yes, we canceled a common factor. Combine like terms? No, we didn't combine like terms. We canceled common factors. Perfect. And that's what they want us to do. So they're telling you what side to work with, and we're completely ignoring the other side, doing nothing with the other side. So in these problems on MyLabs Plus, they're telling you only work with one side, only do one tiny little step at a time, and say the answer for the math, and also say what the step was. If you're stuck, look at what your options are. Either you're going to do a half angle, a Pythagorean, or a double angle. Those are your three options. So it's got to be one of those. Those are your only three options. So, I'm going to do this one as well. It says, prove the identity. 2 tan theta over 1 plus tan squared theta equals sine of 2 theta. To verify the identity, start with the left side and transform it to obtain the right side. So we're leaving the right-hand side alone. Sine 2 theta is being left alone completely. And we're just working with 2 tan theta over 1 plus tan squared theta. Choose the correct step and transform the expression according to the step chosen. So we're either going to use a half angle identity. So if you want, you can look through your half angle identities and see if anything looks familiar compared to what we have right here. And I will tell you, none of it does. Tangent has 3 possible half angle identities. One of them has square roots, the other one has sines and cosines. None of them match this. The double angle identity for tangent looks very similar to this, but it has subtraction in the bottom. And that is extremely important. Automatically, we can't use that. It doesn't match. So what we're going to do is we're going to apply a Pythagorean identity because that denominator, 1 plus tan squared, is a Pythagorean identity. 1 plus tan squared is equal to secant squared. And that's the only thing I'm going to do here, is I'm going to replace my denominator of 1 plus tan squared with secant squared. The top's going to stay exactly the same. My top is going to stay 2 tan theta. Oops. Okay, just a Pythagorean identity in the bottom. Look at your choices. That's the only one that made any sense. And again, anytime you've got a square in the problem, you should think, I might be able to use a Pythagorean identity here. So I've got no idea what they want me to do now. Let me see what my choices are. Apply a co-function identity. Co-function identities have to do with adding or subtracting 90 degrees or pi over 2 inside the angle. I don't see any of that here. That's definitely not going on. Apply a Pythagorean identity. I'm not going to undo what I just did, so I'm probably not going to do that. Apply a tangent identity. I could probably do that. I could probably change everything here into sines and cosines. So the tangent identity would change my tangent into sine over cosine. And then most likely on the next step, they're going to have me change my secant using a reciprocal identity. Because remember where we're trying to get here. We're trying to get to sine 2 theta. And if you think about what the identity for sine 2 theta is, it contains sines and cosines. So now my objective is going to be to turn this into sines and cosines. I bet I'm going to start working this into sines and cosines. So my tangent, I'm going to rewrite it as sine over cosine. So I'm going to have, and this sounds kind of weird, I think I'm going to have a fraction inside of a fraction. I bet they're going to want me to simplify that though. Let's see, let's go over to my paper. 2 tan over secant squared. 2 tan, because they're not going to take a fraction inside of a fraction as the final answer, over secant squared. Tangent is sine over cosine. Tangent is sine over cosine. This is a complex fraction when you have a fraction inside of another fraction. And we can't ever give that as an answer. I'm tempted to try it just to see what it's going to say. But it's because it's so difficult to type on this this little this notepad thing. I'm going to go ahead and fix this. Instead of dividing by secant squared, I'm going to flip and multiply by 1 over secant squared. And this is going to be 2 sine theta over cosine theta secant squared theta. So my tangent turns into sine over cosine. And the sine stays in the top and the cosine goes to the bottom. Let's try that. 2 sine over cosine secant squared. Okay, good. It might have taken our complex fraction, I don't know, but complex fractions are bad algebra, so there's a good chance that it wouldn't. It would give you another chance at entering the answer again. So if it didn't take it, you would be able to fix it and try it again. 2 sine over cosine secant squared. I'm guessing they're now going to want me to fix the secant squared because we're in the process of changing everything to sines and cosines here. And changing secants, secant is a reciprocal function. So we're going to do a reciprocal identity this time. So secant in the bottom is equivalent to cosine in the top. So I'm going to write this as 2 times sine times cosine squared. So the secant squared moves to the top as cosine squared. And then we still have our other cosine in the bottom. Don't get ahead of yourself. I know there's something else that we can do, but they haven't asked us to do that yet. Cancel out common factors. A cosine can go from each piece. There's a cosine in the top, there's a cosine in the bottom. If we cancel one from each, we're left with 2 sine theta cosine theta. Two sine theta cosine theta is equal to sine 2 theta. Sine 2 theta is a double angle identity. Double angle identity because I see a times 2 inside of the angle. Double angle. So let's see here. I was just trying to see how long this was so far. I would really like to do another one. Let me see if there's... This is 7.5? What? All right, so this one says work each side separately until you obtain the same expression. Start with the left side. Choose the correct step and transform the expression. So in the last two examples I did, they only wanted us to work with one side. On this one, they want us to work with both sides. So I'm going to do one more. It looks like it's a fairly short problem though, because if you look at the bottom left corner, it says only 2 parts remaining. So it looks like there maybe is not much to do on this problem. I have no idea where to start, so I am going to see what my options are. Apply a tangent identity. With that +1 in the top, I can't just jump into a tangent identity, no. Apply a double angle identity. 1 plus cosine squared over sine squared. I don't believe that's the double angle identity for anything. Apply a Pythagorean identity. One plus cosine squared is not a Pythagorean identity. 1 minus cosine squared is. So it's not going to be a Pythagorean identity for 1 plus cosine squared. A double angle identity. None of those is a double angle identity either. No, this is interesting. I'm going to pull up my identities real quick because this one has me stumped. 1 plus cosine squared is not anything. It is not an identity at all. Now sine squared we could replace with 1 minus cosine squared. I don't see right now how that's going to help us though. Unless they're wanting us to skip a bunch of steps, I could apply a tangent identity and I could separate this fraction into 2 pieces. I could say 1 divided by sine squared, that's cosecant squared. And I don't know if it's going to like this just because it's so picky. So picky about what it wants us to do. It wants us to do exactly its way. So we've got cosecant squared x. That's if I do 1 over sine squared. And then plus. And then if I do cosine squared over sine squared, I get cotangent squared. I have a feeling it's not going to like this though, but I'm going to try it. At least one of your answers is correct. Write the expression so that it is in terms of a single trigonometric function. A single trigonometric function. I'm just looking through my identities right now. So on this one, they want us to do multiple steps in one. I guess. One plus cosine squared over sine squared. Let's do Pythagorean. And let's just change sine squared to 1 minus cosine squared. And let's see what they have to say about that. They don't like that either. Interesting. I liked my first way. And they don't even give you any help on this one. I'm looking at the double angle identities. And there's definitely no double angle identities for this one that even come close. So it's gotta be. But if you remember back in the problem we just did, if it turns into cotangent, it says apply a cotangent identity. This is number 23. And you know what I'm going to do? I'm going to open this up in the instructor window and see what the answer is supposed to be. And then I'm going to go in and I'm going to make sure that problem is not on your test, because something is wrong with that problem. I might have to look at that's what I did a second ago. Might not show me. Oh, whoops, yeah, show completed problem. Apply, oh gosh. This is a trick problem. That's what it is. All right, so I click on show completed problem. Unfortunately, you guys do not have that option up there, show completed problem. It's just because it's an instructor view right now. This is a trick problem. So what they did is they replaced cosine squared with 1 minus sine squared. They replaced cosine squared with 1 minus sine squared. And then combined the ones and said, well, that's 2 over sine squared. And then sine squared over sine squared is 1. So 2 over sine squared minus 1. And then 2 over sine squared, they used a reciprocal function and brought the sine squared up as cosecant squared. But that's kind of silly because they said they're going to work each side separately, and they didn't. They just worked with the left and made it match the right. So I'm going to make sure, so this is 7.3.21. I'm going to go ahead and make sure that this problem is not in your test. And I really do not like solving these proofs in the computer at all. So you shouldn't expect to see too many of them. I know your test is not open yet. I'm going to go and review your test one more time just to make sure that it's not too crazy. Make sure something like this is not in there. So I'm going to go review it real quick and actually have it open here in the next few minutes and push these videos out to you. Sorry about the crazy last 15 minutes, but I'm really, really glad that I decided to look at this last problem, because sometimes I look at a problem and I say, oh yeah, that problem looks great. No problem. Just use some Pythagorean identities, and then it doesn't work out any way that I think it's gonna. And especially with these types of problems, when MyLabs Plus won't let you do it any way except for their way. If you don't do it their way, that's wrong. It's really unfair, I think. And I very often go back in and I will give partial credit for these. So on your test, for these proof problems, if you're struggling with the proofs, just don't leave the answer boxes blank. Put something in there. Even if you could do these out on paper, put some of your intermediate steps into the answer blanks so that I can see that you do know a couple of intermediate steps on how to get from the beginning to the end. I will give you credit. So don't leave those boxes blank. Even if it's not what MyLabs Plus wants, put something in there on how you get from the beginning to the end. Okay? And use those options in the drop-down list to help you along the way if you get stuck. See what your options are, because they'll narrow it down. They'll say, use a Pythagorean, use a cotangent, or use a double angle. Those are your only 3 options. You got to do one of those. So they'll narrow it down a lot for you. So I'm going to go in and I'm going to just take a second glance through the test, and then I'll have that open for you. I will definitely make sure that this is not on there or nothing like this is on there. Email me anytime, day or night, any question you have. Some of you guys email me and then apologize. Please don't do that. It's what I'm here for, is to help you in any way, shape, and form that I possibly can. I am happy, more than happy, to answer any question that you have. If you've got 10 questions, send them to me. Send me all 10 of your questions, and I will sit down and I'll make you your own personal video. I will write out all of your problems step by step, tell you exactly how you need to do them. I just want to make sure that you're not trying to get me to do your work for you. I want to make sure that you have attempted this stuff and you are honestly stuck and need help. So put forth your best, most honest effort. You are stuck, you come to me, I will help you. No problem, hands down. I'm happy to do whatever I possibly can to help you through this. And good luck on your test. I will be in the Math Tank on Monday, and I will be in the Math Tank on Wednesday. And if you need any help, come and see me. Email me. I know some of you don't come to campus regularly or live close by. So just keep those email questions coming, and I will be happy to also help through email. Good night.